Alright, this video is going to do several examples of derivatives of inverse trig functions. So this page here is the summary of them, and it pays to have those in front of you when you're working. The thing to remember is there's really only 3 equations you need to memorize, because sine and cosine are the same except for the negative. Tan and cotan are the same except for the negative, and secant and cosecant are the same except for the negative. So we'll keep that in mind, but we'll drill those into our heads and make sure we get them. All right, first example is, let's take this function. Y equals 4 cosine, whoops, let's go back, cosine inverse of t minus 10 tan inverse of t. Well, we look at our sheet, cosine inverse derivative of it is negative 1 over 1 minus x squared, right? And derivative of tan inverse of x equals 1 over 1 plus x squared. So let's try that. This 4 goes along for the ride. Cosine is negative 1 over, and this is t here, so it'll be 1 minus t squared, minus 10 goes along for the ride, and the tangent is 1 over 1 plus t squared. So that's really all that's going on for this particular example. That's A. Let's try another one. B. Y equals the square root of z times sine inverse of z. So here we'll have to use the product rule, right? Which is f prime g plus f g prime. I like to rewrite z to the 1/2 instead of the square root, because to me it's easier to differentiate. So we'll do the derivative of f, which is 1/2 z to the negative 1/2 times g, which is this, plus z to the 1/2, that's just f, times the derivative of g. So the derivative of sine inverse, if we go back, derivative of sine equals 1 over 1 minus x squared. So it'll be z squared over, right, 1 minus z squared. Alright, so if we want, we can simplify this a little bit, because this will go in the denominator. I have a 2 down here. I'll put the square root of z in the denominator, and I'll have sine inverse of z. And then this will be plus, I can do this, oops, that's a z over 1 minus z squared. How much you simplify, that shouldn't be the biggest issue. I'm hoping that the prof is looking for the fact that we know how to do the derivatives. Alright, because this is just a little bit hairy looking. Alright, let's try another one. C is x squared, well, say y equals x squared times the sine inverse of x. Alright, and again, the sine inverse, the derivative of sine inverse of x equals 1 over the square root of 1 minus x squared. Product rule, f prime g plus f g prime. So the derivative of x squared is 2x times g plus f times the derivative of g, which is 1 over the square root of 1 minus x squared. Really not much else you can do with this one, is there? Not much. This next one is a little bit more complicated, but it's good practice. So y equals 1 plus the arctan of x over 2 minus 3 arctan of x. Remember, arctan of x, all that is the tan inverse of x, right? Same as arcsine of x is the same as the sine inverse of x, etc. This will be the quotient rule. So if I call this f and this g, the quotient rule is f prime g minus f g prime over g squared. Alright, so we're going to start with the derivative of the top. Well, the derivative of a constant is 0, but then the arctan derivative, or tan inverse, is 1 over 1 plus x squared, right, times g minus f times the derivative of the bottom, which is the derivative of 2 is 0, and it'll be negative 3, and it's 1 plus x squared. So let's see what we have there. This is all over g squared, but let's look at what we have on the top. We have the same denominators here, don't we? So we will have 1 plus x squared on the bottom, but this will become 2 minus 3 arctan x. I'm going to distribute this over here, so it'll be negative 3 and negative 3, won't it? So if I distribute negative to a negative 3, it'll be plus 3, and a negative to the negative 3 arctan will be plus 3 arctan x, right? All over the g squared. Well, if I divide this all by g squared, it actually will move into the denominator here. Alright, and then this and this cancel out, and we have 5 over, whoops, that should be in parentheses, 1 plus x squared, 2 minus 3 arctan x. Alright, that was a little crazy, but it worked. It's just a matter of not losing signs, right? Alright, let's look at another example. This one is, I'll call it E. Y equals arc secant x times arc cosecant x. Woo! So let's see. Y prime. This is a product rule. F prime g plus f g prime. So sorry about that. So the derivative of arc secant, so the derivative, oh my gosh, I'm sorry. It keeps wanting to do that when I hit it. So the derivative of secant inverse is 1 over absolute value of x, x squared minus 1. And the derivative of cosecant, guess what? We said is the negative of that. So, arc secant, 1 over x, x squared minus 1. And I didn't put the 1 up there because when I multiply by g, this will sit on top. Arc cosecant x plus arc secant x for the derivative of this one, which is a negative, I'm going to put that negative here, x squared minus 1. Now, this is pretty good to simplify. This is good to simplify. We have the same denominator, notice. So we can bring the numerators together. Arc cosecant x minus arc secant x all over x squared minus 1. Alright, how is that? Pretty good? Looking for a few more that I can show you. Let's go to a new page. Alright, here's another problem. We'll call this one F. So if we have y equals 2x plus 10 arc cotan x. Alright, well, we can do the derivative of this first part, which is just 2, right? Plus, the 10's going along for the ride, but what's the arc cotan? Got to get my arc cotan sheet out here, and it's negative 1 over 1 plus x squared. So if I want to put this all over a common denominator, which is this one, I'm going to multiply the top and the bottom by this, right? Then it'll be minus 10. So let's distribute. It'll be 2 plus 2x squared minus 10 over 1 plus x squared, which equals 2x squared minus 8 over 1 plus x squared. Well, let's say they ask you to solve when f prime of x equals 0. All right, so we're going to take f prime of x and set it equal to 0. Notice the denominator will never be 0, will it? So we only have to consider the numerator. So 2x squared minus 8 equals 0. Notice I can pull a 2 out and I'll have x squared minus 4 equals 0. I get rid of the 2. X minus 2 Alright, sorry about that. I don't know what in the world happened. So x minus 2, x plus 2 is the factoring of that. So x will equal plus or minus 2 when the derivative is 0. They want to know, solve it when the derivative is 0. So we set that derivative equal to 0 and solved for x. All right, that was kind of a crazy one, but let me give you one more example. Let's say we have f of x equals arc sine z plus arc cosine x. Let's see what happens if we take the derivative. Well, arc sine is 1 over 1 minus z squared. Arc cosine, that would be plus, but arc cosine is minus 1 over 1 minus z squared. Notice what we get. This minus this is 0. So this is a funny one. Turns out the derivative of itself equals 0, which means this here was probably a constant, right? Because isn't the derivative of a constant 0? So that's something we haven't encountered yet. Now, I'm going to stop here, but this is a good practice on the inverse tan derivatives.